Good morning, everyone. Welcome to Big Data today. So 2 weeks ago, we had our first lecture. And as usual, I'll start with a quick revision of what happened in the previous lecture, and then we'll advance today. So in the last lecture, we looked at something we notice daily, that the amount of data around us that we are recording or analyzing keeps growing very, very quickly. And nowadays, we store data largely digitally. Until the 90s, early 2000s, there was actually a majority of analog storage on tapes, but this has definitely changed. And the three V's are very important as a characteristic of big data: volume, variety, velocity. And we saw the term big data is not new at all, comes from the 90s at least. And we looked at a couple of other examples, how the amount of data keeps growing. And in this course, we want to prepare you for a real world challenge, because in the real world, you will not always have small data that fits on your computer or your RAM and that you can process all of your data and train your models on your laptop, but rather you need a different environment for this, because your computer and your RAM will just be too small to store all the data in a large big data task. And so you need a different environment, be it a big server, a distributed environment, whatever. And you also need to run the training in such an environment. We then looked at the organization of the course, and in a couple of weeks, I will open in iLearn that you can pick your seminar topic. But since I see how many students are enrolled in the iLearn course, and how many are here and how many are watching the recording, there was also an update that this year your marking is obviously about the seminar presentation, but the Q&A session so far always covered your presentation. Now it will cover potentially everything from this course, because I simply want that students also attend the lecture or watch the recordings and not just wait for the seminar presentation. The Q&A may cover everything from class. I will maybe not quiz you on tiny details or ask you to enumerate 10 things yet. I want you to be able to attend this course and have some incentive, and the Q&A session may refer also to any other part of the lecture. And same announcement in all the other courses this term, because I'm I'm offering the recordings through YouTube, and I can see the statistics of how many people actually watch these recordings. And it should be more, in addition to the ones who are here in the course. But I'll say more about the seminar in a few weeks. We looked at some examples like Uber and others, and we saw how the worldwide economy is being changed, and market capitalizations and so forth due to big data and AI. And we talked about a few things I worked on, for example, at CERN, and their work on electricity theft. And then we said we want to build big data architectures. We want to work with big amounts of data. So we probably need to do this in a parallel way. And parallelism is something that some of you may have seen, like in an introductory operating systems course. But this course is taken by lots of different students, and not everyone may be familiar with a lot of details in parallelism. So in the last lecture, we looked at processes, threats, concurrency, and parallelism, especially these two terms, concurrency and parallelism. Sometimes they get used as synonyms or they get mixed up. So we discussed how we can define them as one attempt. And there's a very good Stack Overflow article. Or who of you had a look at the Stack Overflow one? So did you find the explanation and the examples reasonable? So this is the best explanation I found about this kind of stuff. So that's why I'm linking here to the Stack Overflow one, and quite a few of you have read it. I came across that quite a long time ago, but I think I didn't see any better explanation, at least in a readable format. So I think this is here where we stopped last time, and now how do you deal with multi-threading or parallelism as an end user? Do you have any examples? Not as a coder, but when you use your computer. I don't understand you. Playing a game, so where do you see parallelism in the game? Okay, loading a map. Okay, any other examples? Mhm. So multiple tabs in your browser. They may run as a thread, they may run as a process, uh, depending on the browser. But yes, you need some parallelism because you still want to be able to read some other page while YouTube keeps playing music. So a lot actually in user interfaces. Also, if you run a very long task in a program and you want to be able to abort the task, you need through the user interface, you need some kind of multi-threading so you can actually click the stop button, because otherwise this you won't be able to click the stop button. One person here says Windows services. Okay. Yeah, I think all of those are great examples. And when you start building your first user interfaces and you don't use multi-threading, then these buttons don't work when the computations run in the background. Um, while we all take this for granted, it was not like this, I don't know, 60 years ago or something, or 50 years ago. Probably even multi-processing was not really there. You just had operating systems. They could run one program at a time or something like this. But now we all take it for granted that we have lots of processes running in the background. So a lot has actually happened, but it comes with new challenges. And our hardware nowadays has multiple cores and other tricks. So we actually are able to use hardware that offers parallelism. Uh, we will now look at a quick example. What I want to do with you is we'll see a very simple example of how you can do parallel work in Python. Whether it's multi-threading or multi-processing, this is something we discuss later, but we will actually work now with a thread pool. Has any one of you used a thread pool in Python? What have you used it for? Okay. Okay, so you saw it in your programming 2 lecture, but it's a very diverse lecture with students from different degree programs, and only you have seen it or remember it, and the others haven't raised their hand. What I want to do is, we have a lot of URLs, and we want to download them. And now, if we do this in a traditional way, so without parallelism, but I have a list of URLs, and we can try this in the terminal. I will amend the screen share in a moment. Just bear with me. So I have something like this. I have various URLs and I want to download them. And we can try to start implementing this. In Python, I will need a few helpers. I need to import the URL lib request. And then from Python, we actually want to do multi-processing later. We want to import the pool and call it thread pool. Now, how can I actually open a URL in Python? Who has done this before? Open a URL in Python. Quite some. Okay. Many have not. It's fairly easy in Python. This is the good thing because we have this URL lib request and we can just call URL lib request dot URL open. If we wish, we could do it like this. But now opening a URL may take a little bit of time for technical reasons. How long do you think it would take to open these? So this is 10 or 15 URLs How long would this take if we do this in sequence, step by step? Yeah. How many? Around 50 seconds. Anyone thinks it can be done a little bit quicker? Can we do this in like half a second? Yeah, 30. Something like 30, 50, whatever, maybe 10. But it will not just run in 1 millisecond because we have all these delays in the network. But most of the time, so if we do this now sequentially, say we open one URL, then the next URL, then the next URL, actually our computer is just waiting most of the time for the network. It's not like that opening these URLs keeps our computer that busy. It's rather the network, which is slow. So we are actually super slow in downloading this. And that's why we want some kind of parallelism. We want to request one URL and in parallel the second one, the third one, maybe three in parallel. And once we have one, we request the next one because our computer is really not waiting most of the time. We're waiting for the network. And we will try to implement this now. And the beauty is in Python, this is super easy. So we can say we call this open URLs, and we have the number of threads, and we instantiate our thread pool because the thread pool will exactly do that for us, that we don't need to spend a lot of manual work on creating threads. So a thread pool, in the simplest case, a thread pool with one thread is nothing special. But with two threads, the thread pool works this way. It creates two threads, and we can assign tasks to these threads, say download 100 URLs. So the first thread does that, and the second one, they pick from that list. And once one thread is done, it grabs another URL from the list and so forth. So we have a certain number of threads at the most, and they are running in parallel. And so we instantiate the thread pool, and we say our results is, we call the pool and say, we have a map function, and map here means we are passing a reference to a function, and we pass that list as the other reference or as the other parameter. And then this thread pool will run. And eventually we also need to close it, but that's just a little bit of extra stuff. So, and now we can run this thread pool and we can say, just checking how I implemented this before. So, do you know this function or this feature here in IPython, percentage time? Has anyone used this before? It's quite helpful if you want to run a task in IPython and you wonder how long it takes. You don't need to, measure the time before and after, but this is rather done in IPython for you. And we will call open just wondering because the tab here is not returning it. If there's any typo or something, we'll see. So why doesn't this work? Try it again. Seems, URLs, not URL. And now I'm calling the thread pool just with one thread at a time. So it took about 8 seconds to download this. And how many URLs do we have? 12. So you guess 30 or 50, but it depends a bit on the network. But more or less, no one guessed it would take like 1 year, and no one guessed it would just take 1 millisecond. We could add more URLs. It will take a little bit longer. But still, with these 8 seconds, actually almost all the time, we are waiting for the network. And this is something we can also see here, that actually most of the time the CPU hasn't done much, but we were actually just waiting most of the time for the network. So we can try to parallelize this now, and we will attempt it with two threads in the pool, and it takes around 3 seconds. If we repeat it, so there is some uncertainty in it. It runs around 3 seconds plus minus. Sometimes it takes longer just because of delays in the network. So we see it's actually quite an unreliable estimate. 2 times now, it took 3 seconds, once 6 seconds. Try it again once more. So we have delays in the network and not a very reliable infrastructure to measure this reliably, but around 3 seconds. We can increase this now to 4. How long will it take? Approximately around 2 seconds. So we see we can already massively speed this up. And now imagine we don't have just 12 URLs, but we have thousands of URLs, and we use a thread pool maybe with 40 threads. You can imagine we can massively speed this up. And this is something, this thread pool, you can use it for lots of different stuff, not just for downloading, but rather you can use it for any function that would process some data. And you can just pass the function reference here and it works. And you don't need to create manually any kind of threads. If you create threads manually and you need to synchronize them or you need locks, whatever, all of this is quite complicated work. And if you use something like this thread pool, it's just parallelized for you and you have little work to do. When I ran this some years ago from at home, I think I can quickly share this. Took something like this. It took 9 seconds and then 4 seconds and so forth. So very easy actually to get a massive speed up here. If you want to learn more about how to create threads in Python, there are some very good references I found here on the internet. And I'm also using, or I'm inspired by some of that material. And we will now look at a couple of challenges that we face when we try to do parallelism in Python. We will now code again something. So today it's lots of interactive coding. There's one person who wrote me as a private message that time measurements are not always the thing you should trust. And that's absolutely fine, because for this we have complexity measures, because yes, we have all of these things that can influence the measurements, like here the network delay, whether we run other tasks on the side. And that's why we often care about, as a first estimate, or as the first thing we optimize for is complexity. But still, at the end, even once you have your complexity, the running time is something you should not underestimate, because that's eventually how long it will take for this to run. But there's more or less a trend. If you have low complexity, the running time also tends to be lower. Not always, as you know, but overall, always aim for good complexity, and good running times typically follow. But when we look at this multi-threading here, and I want to show you a couple of things, and we see if it actually leads to speed ups or not. We will again do some coding. We will import the time module, and from threading, we will import thread. Yeah. Try to make it bigger. Is it better like this? Okay. Just making the window smaller. Good. And what I want now with you is, well, unfortunately, when I resize, then this stuff is not visible anymore, because this is the issue with IPython, but fine. What I want now is, I want a countdown. So this is 50 million. And I will write a function that does a countdown for n. And actually, we will just build a loop, and we say, in each iteration, we will decrease n by 1 until it stops. We will count down from 50 million. For those who are in the classroom, you just see my slides where I had where I had run this. When I ran this before, it took about 2 seconds when I ran this on my old computer. Now let's see with the new computer how long it takes. Maybe you can try this in parallel. You can open your IPython and just code the same. We see how long this experiment runs on your computer. We first run it now in a purely sequential way, and then we will try to parallelize it. And we will see some unexpected effect in Python when we later try to parallelize this. So what we do now is we measure our current time. And here it's very important, if you code this as well, don't run as a single line, just start, which is your current system time, and then you keep coding, because this will deliver you a wrong outcome. Because if you run one line, then it's measured and maybe it takes you half a minute to code, and that means the running time that you measure is not correct. So in IPython, at least on my Mac, I can use the keyboard and type Control O, and then in this interactive session, I can type the next line, and we can run the countdown, and then we measure the time again. We'll run this. So it's already done, and we can just subtract n minus start, and we see, well, on this computer, it took like 0.74 seconds. When I created this and ran this for the first time with my previous computer, it was 2 seconds, but Python versions change and so forth. So who of you is running this at the same time? How long does it take on your computer? Some of you have opened a computer, so give a try. And the limit of Python will come later. We don't see the limit of Python here for this single thread case. Who is right now in the classroom typing this as well in your IPython? Okay, I'll give you a moment, and then we'll see how long it takes. And since the computer is a new one, I'll actually just increase this with another 0, and I'll run it again. So we make this then 500 million rather than 50 million. Yeah, 500 million. Then we run it again. So increase it to 500 million. It takes on this computer 7.3 seconds. One person asked why I use the IPython and not the Jupyter Notebook. You can also use the Jupyter Notebook if you wish. But just to run some small scripts, I prefer the IPython in the terminal. It's not running in the browser, which comes with lots of distractions. Maybe then I see some tab in my browser with emails that I want to look at. So usually I just like to close the browser. And for me, it's personally easier to use the IPython, or I'm more efficient than with the Jupyter Notebooks. But the Jupyter Notebooks is just an extension of the IPython. So who has run it?
My computer is not that good. It's almost 4 seconds for 50 million.
Okay, 4 seconds for 50 million, and then we can assume it's 40 seconds for 500 million. Anyone else has run it? For 50, okay. I'm also surprised it's running that fast on the computer, because the old computer was 2.2 seconds, as I see in the screenshot, and now it's 0.7. And that's why I increased it to 500 million. But you mentioned with 50 million. Okay. Now we could think in Python, we will change this a little bit, and just hiding the stuff that is from the slides visible on the projector, because this is my notes, what I can type now. We could think about parallelizing this now. What we have is our countdown function, And we could now build two threads. We could have one thread counting down half of this and another thread counting down half of this, because we have multiple threads or multiple cores in our machine. So two threads, you would think this gives a speed up, right? Let's test it. We will create a thread in Python. We say the target, target is a parameter, which is our countdown as a reference. And so just need to look that up for the syntax. The args is we take our count and divide it by 2. And don't forget this comma, because the args is supposed to be a tuple. So if we put these parentheses around it, it's not a tuple yet with a single entry. So we need to put this comma there. And we're just doing the same with another thread. And each time we're just reducing the count or halving the count into 2. So we've created 2 threads. And now again, let's run this. We want to know the time. We want to start thread 1. We want to start thread 2. And eventually we join them when they are done. And then we measure the end time. It's very important you run this as one block, as I said before, or if you use Jupyter Notebook in your browser, also run it in one cell and not in 2. Otherwise, all the time you're waiting and not working will count towards the end time. So my count was 500 million. Before it took 7 seconds, so we would assume now it's around 3.5 seconds, right? If I split the count into half, more or less 3.5 to 4 seconds. Who thinks that that's the case? That we about need half of the time? Maybe raise your hand if you think this looks plausible. And it looks plausible, but let's see what's happening now. Doesn't seem to run much faster. Let's see what the time is. End minus start. It's still 7.2 seconds. So it didn't lead to any speed up. If you did this in a language like Java or C++, you would feel a speed up. And this is where we are coming to a limitation in Python. You can also run this on your computer that you see I didn't make this up, but it will also not lead to any substantial speed up on your machine. And there is something that is the reason for that. It's the global interpreter lock called GIL. Who of you has come across the global interpreter lock in your programming 2 course, I guess? Okay. I taught the programming 2 course in the past, but not in the AI program, but in the cybersecurity program. And there we discussed such stuff too. But then someone wanted to teach it in one of the AI programs, and I think took a copy of the slides and amended it. But we have lots of other students here who didn't take the programming 2 in your program, because we have other programs too and exchange students. So we'll discuss it now. And the global interpreter lock is a limitation in Python, because multi-threading is messy in general, not just in Python. In every programming language, multi-threading is complex because you can run into all sorts of strange problems. Imagine you have 2 threads, they share memory, and then one thread works on the memory, another one works on it, and they could corrupt the memory. Maybe these threads are waiting for each other. So by using some locks, for example, that you lock some part of the memory and you can only enter that piece of code when the lock is not on and some other thread is in it and may go out and then release the lock. So this is one way how you can try to prevent leaked memory by using locks. But sometimes threads are waiting for each other and you're running in a deadlock. So this is overall something that can happen in every programming language where you deal with threads. In Python, This could also happen, but work was done that you cannot run into this kind of leaked memory issues. Because in Python, there are locks, and concretely, there's the reference count variable and or the reference count of a variable. And this one can be kept safe by adding locks to all data structures that are shared across the threads. You could do that, but Python, at least the CPython implementation, puts one big lock on the whole interpreter itself. And by doing a very high-level lock and not a lock down on the individual data structures, you're eventually not able to do multi-threading in Python. So why was this global interpreter lock created? Because first of all, it slows us down massively. Just asking quickly the students who are here online if you can still hear us, because there was just some interruption in Zoom saying it switched somehow speakers. I don't know how. Maybe the ones who are online, just confirm quickly if you can still hear me. Okay, good, because there was just some glitch here in Zoom. So this global interpreter lock is something that faces lots of criticism in Python, but also some praise. Because in the early days, when Python, or when the concept of threads was added to Python, the developers did not want leaked memory. So they felt the easiest way to prevent leaked memory. It's the HDMI, thank you. We'll try to make the HDMI work. Good. Was that down the whole time or? Okay. So that was maybe why Zoom warned us about some of the audio, but we are back. That's actually a beauty from teaching from at home. I don't need to worry about HDMI cables and all of this. So the developers of Python, they didn't want these multi-threading issues like leaked memory and so forth. And they felt the easiest way to prevent this would be to put a lock on the whole interpreter itself. And Python is actually quite old. It's from the old days when some operating systems even didn't have the concept of threads. So the concept of threads was actually only added later. And a lot of Python libraries, they rely on some super old C libraries in the background, because there are lots of old C libraries with all sorts of features that we use every day through modern libraries. And if you allowed multi-threading, you would also have to update these old libraries in the background in order to be thread safe. And that's something that didn't seem possible at that time. So they felt the easiest way to prevent leaked memory is to add the global interpreter lock. It was easy to add, and a lot of these old C libraries could be integrated. So that's actually a good reason for the global interpreter lock and why it was added many years ago. You can just re-implement the example from before, not using multi-threads, but multi-processing. So that's definitely possible in Python. So you use the multi-processing library, and you just re-implement what we did before. And it's more or less just the same code. We have a count, a countdown function, and we use now a multi-process pool, and we just run these processes in here. It's just a slightly different structure what we apply. We pass a reference in a list, not a tuple. But it's more or less just the same, but with multi-processes. So we could run two processes, and yes, this will run eventually faster. Because for each process, I would just pass half of the countdown, and then I have true parallelism. But using the multi-threading doesn't work in Python because of the global interpreter lock. If you create processes, this comes with some extra load because you need some extra work to create the processes. And processes, I saw you. Processes, when you use two processes, you cannot have leaked memory because two processes cannot share memory. So with memory, we mean the RAM. You can have multi-process communication if you wish, if you want two processes to interact. That's a different topic. But with processes, you don't run into the issue of shared memory or leaked memory. But there's still actually a reason we would like to use multi-threading, because threads are low weight, they're easy to create, which isn't expensive, but we still have the leaked memory issue. So we need to find some compromise. Yes? Because you may be able to turn off the global interpreter lock. And what I said before with the global interpreter lock, it's something in CPython. So CPython is the implementation most of us use, but there are other ones like Pythons or Java-based running time. And there are various other Python implementations like PyPy, Python interpreter implemented in Python. I don't know if you know all these derivations of Python, and not all of them have the global interpreter lock. And we could turn off the global interpreter lock, maybe. But that's something we'll discuss now. So I think in the old days, when the global interpreter lock was added, which was probably sometime in the 90s, it didn't bother too many people because a lot of computers only had one core. You could obviously do multi-threading because of concurrency, but there was no big data world yet or CPUs with lots of different cores. So it didn't bother too many people. At that time, probably the global interpreter lock looked reasonable. But now in the big data world, and we have different CPUs today, we need more parallelism. So there has been a lot of discussions over, I think, the last 15 years, if the global interpreter lock should be removed. And there are some pros for it. Yes, we could use proper multi-threading, but cons is, what about all this leaked memory and all these old libraries that need to be rewritten? And it can happen if you change the locking system, so you don't have a lock on the interpreter, but more finer locks on data structures. It could happen that in such an environment, you actually have single-threaded programs that run faster than multi-threaded programs because of all these issues around the locks. So that's also something that could lead to issues, that maybe I just have a single thread, but I have changed my whole interpreter environment and it runs slower than before. Maybe something we don't want either. One person claims the HDMI got disconnected, who is in the Zoom, so the HDMI shouldn't be your issue, but I can reinitiate the screen share. Does it work now? Okay, I don't know for how long this was off, because for me it all looked fine, but with stuff like this, just ping us. In the world of open source, there's this term of a BDFL. BDFL stands for a benevolent dictator for life. So the guru who runs an open source project. And in Python, this is Guido van Rossum, or he was the lead person of Python for a long time. Now he's less active, I think. So he was the guru who came up with Python and ran the project for decades. He was asked about removing the global interpreter lock some years ago, and he said he would be very happy to see someone who can remove this global interpreter lock, but his condition would be he would like to see that a single-threaded program still runs as fast as before if you make major changes to the interpreter. I actually saw Guido van Rossum live once. This was, I think, in 2015, so 10 years ago, when I was in London for my master's. And Guido gave a very good speech. The lecture hall was super full. People were queuing outside, and, a very technical university with lots of nerds who were happy to see Guido van Rossum. And this was actually one of the questions that was raised: when are you going to remove the global interpreter lock? And he said he doesn't know how to remove it in a reasonable way. He's just waiting for some genius who would come up with a solution. So that was what he said. And meanwhile, a few things have happened. I mentioned before the different Python implementations, like we usually use CPython on our computers. There's Chython, a Java-based running time. There's IronPython. There's PyPy. So Chython has no global interpreter lock. PyPy has one. But in Cython, so Cython is not CPython, very importantly, totally different implementation. So Cython is actually something in which you write Python code, and it's compiled into C++ code, more or less. This is Cython. It exists, but it can be temporarily disabled. So depending on which implementation you use, the thread class actually makes sense. And it turns out last year there were some news. And these news just came out, or I just noticed the news when I started teaching this course last year, and I just updated the slides. Last year, CPython 3.13 was released. And with that one, it's actually super easy to disable the global interpreter lock. There's a flag, but it's not a running time flag. It's a build time flag. So when you build your own Python distribution, when you compile it, you can pass to the compile process this disable global interpreter lock flag. And then you actually get two application binary interfaces, so two outputs from the compiler, one of which global interpreter lock is on and one where it's not. So it's not a running time flag, it's a compile flag. I don't know, has any of you ever built your own Python running times, so that you build your Python interpreter from scratch or from source code? So if you ever want to do this, I've done this a few times, not often, you could pass this compile flag, and then you actually get two ABIs, so application binary interfaces, one with the global interpreter lock, one without. And currently it is planned that in the next few releases of Python, so in the next 1 or 2 years for CPython, you would have a runtime environment variable. So when you actually launch the interpreter, you could turn this on or off. Initially, they want to have the global interpreter lock to be on, but you could pass a flag to turn it off. And another goal is in the next few years, so towards the end of the decade, CPython would switch the global interpreter lock off by default. So we're currently in a transition phase. So this takes a few years. Why does it take a few years? Because of backward compatibility and all these Python libraries that use in the background some old C libraries, they should have a few years for transition, so that they step by step migrate their libraries in order to make them thread safe. And then in the next few years, by default, the global interpreter lock would be turned off, but you could still turn it on if you wish. So this is the goal for the next few years. And then maybe sometime in the mid of the next decade or something, maybe the global interpreter lock doesn't exist at all anymore, and at some point it would just be kicked out. Let's see. So it's a transition phase, and library developers are looking into this. And once that transition is made, then the thread example we looked at will run faster. It could already run faster. So if you don't use CPython, but for example, Chython, or if you build your own Python distribution, if you wish, from source code, you could turn the global interpreter lock off and then run the example that we run faster. For that example, it's not an issue, but it would be an issue if you actually have lots of shared memory, because then you would need to do some extra work on that, like adding locks and so forth. So let's see how all of this will evolve in the next few years. It's an interesting time. Now the question is, how much parallelism do you need to know in practice? How much do you need to know when you code? And I'll first of all wonder, what do others say? So there's a very famous computer scientist, Donald Knuth, or how to pronounce his family name. So he wrote these famous computer foundations of computer science books and did a lot of contributions to computer science. He also is the inventor of TeX, which is the basis of LaTeX. LaTeX is just an extension with more macros. So he did a lot of fundamental work in computer science. And he was asked a few years ago how important parallelism is. And he said something, let me put it this way, during the past 50 years, I've written well over 1,000 programs, many of which have substantial size. And he says he can't even think, or he can't think of even 5 programs that would have been massively run faster if you added parallelism or multi-threading. So he doesn't see much impact, but he says he thinks it from his view on TeX or LaTeX that this would not run faster. He doesn't see how this could be parallelized. It's a very linear process to typeset these documents. But he says he's aware that some form of parallelism exists, like rendering graphics, breaking code, scanning images, simulating processes, nowadays more machine learning, but he believes that all of these applications require very dedicated code and special purpose techniques, which would have to be massively changed every few years. So this was a few years ago. I think parallelism has become more important, especially now with AI, and we have better CPUs with more cores. Yet I think most code that you ever write will not run in a multi-threading way. Probably it will be sequential code. And I guess most of the programs you have written so far are sequential, right? It's the same with my code that I wrote. What you will notice in practice when you write your own multi-threaded code, you will face lots of challenges like shared resources, synchronization. And it turns out that even at Google, they noticed 20 years ago that even though they had thousands or tens of thousands of smart computer scientists, even most of them struggled to write multi-threaded code that worked well. So they came up with a solution that you don't need to do this on your own, but we'll see this either today or in the next lecture. But something that you will see as a machine learning practitioner is that a lot of APIs that you would use, they use multi-threading or parallelism under the hood. So they encapsulate this to you through a high-level interface, and you can use this from a very abstract perspective. For example, in scikit-learn, say you want to build a random forest classifier with 100 trees, 100 estimators, and you can pass a parameter for the number of jobs. Who has ever done this in scikit-learn, that you pass a parameter for the number of jobs? Okay. What number would you put there? 5, okay, maybe 5 cores. And this is where the hesitation starts. And now imagine you get a new computer with more cores, you need to update that number. Doesn't sound good. What you can do is you can just pass -1, and then it picks the number of cores that are available on your machine. So if this is probably the easiest that you could do. So the library quickly just reads from your operating system how many cores your CPU has, because you shouldn't put a massive number in there. Say if you have 4 cores, you should not put in 100 or 1000, because you're just creating too many tiny threads that are competing with each other, and most of the work gets lost on synchronization of the threads and on the scheduling. So rather you would put some reasonable number, maybe just a number of cores, and that one keeps changing as you get a new machine. So just put in -1. That's something that I did. During my PhD time, I had the chance to work with a very good server that the lab bought. And in the first few weeks, it wasn't available to the other lab members. So this was something in 2016, 2017, so it's quite a while back now. But we bought that server for the lab where I did PhD, and the machine had had multiple CPUs, in total like 140 cores or something, and like 1 TB of RAM. So that was lots of fun, and it was even more fun nearly 10 years ago because it was even more special. And what our IT admin then wanted to do is to set up some virtual machines that you can, reserve some of the time. But I think he was on vacation or didn't have time. And then I just had exclusive access to the machine, no virtualization. I could just run my code there and put in a -1, and the -1 meant like 140 cores and something like this. So this helped me to run even better experiments for a paper. And when he came back or had time to set up the machine, I was done and didn't need to share the resources. Because if you have 140 cores, it's fun, but if you need to share it with 20 people, it's not that much fun anymore in the lab. So just ran all the stuff before it got set up, and it was fun. Internally, things like scikit-learn, they use choplib. It's a library for parallelism. Concretely, choplib, and also what you would do in scikit-learn, then it uses multiple processes to do the work, because multiple threads, we saw it doesn't work, or you would try to disable the global interpreter lock. With some other libraries in the past and sometimes there were some hacks how they could temporarily pause the global interpreter lock, but none of that is too reliable. So the choplib is a library in Python, or a module or package that is actually quite helpful, and you can use this quite easily. And yeah, some classes of scikit-learn, at least in the Python environment, not CPython, Python, they release the global interpreter lock internally with some hacks, but not too great eventually. So the choplib probably works better. There's also a totally different approach to writing parallel code. It's asynchronous programming, and asynchronous programming is a form of parallel programming that allows a unit to run separately from the primary application thread. So you have your primary application thread, and you can sort of branch off with a separate entity. And when this work is done, that separate entity notifies the main thread. And this asynchronous programming often leads to improved performance and enhanced responsiveness. And it's also supported nowadays in Python by the syntax. So you have this async statement, and you have these await statements. And with this, you can actually do asynchronous programming in Python quite easy. Has anyone of you ever done asynchronous programming? Okay, what have you used it for? Okay, someone else raised their hand. Okay, calling OpenAI. Okay. But we're not discussing the asynchronous programming here in detail. It's just one more note. If you want to learn something in addition, take a look here. There's a very good tutorial on realpython.com on this. Because the parallelism, this was more like a revision or extension for those of you who may have heard this before in your programming 2 course. Some have not. And now we have all the foundations to actually work towards big data architectures, for which we need parallelism. We will look today and next week into distributed systems, which are the basis of big data architectures. We will look at the MapReduce theorem. That's something proposed by Google that has now lots of variations and is used in lots of infrastructure. We will also see there is a fundamental limitation in distributed systems, the so-called CAP theorem. We'll discuss this, and we will see how we can use specialized hardware to speed up big data architectures. In order for you to fully understand what we are doing here, you need to be familiar with database management systems. Are you all okay with not just database queries, but how the database management system works behind? Who feels okay with this? Not too many. So it's more than just SQL statements. So that's why, because I know it's probably not everyone is too familiar with this, we will briefly do a quick revision, and we look also at some essential guarantees of relational database management systems, and then we will contrast this to other guarantees in big data environments, and we'll compare them a little bit. So when you run SQL queries on a database, you're not accessing the database directly, but rather you have a database management system in between. Somehow, this data that you use in your database system is represented in the database in an internal schema. Typically, we don't care about this. We rather care about the conceptual schema, which are the tables we look at and the different rows and the types of rows and keys and all of this. And this is the one we query with our SQL statements, and we build these external schemas. Do you know which data structure is used in the internal schema to represent your tables in a database system? Because you don't just have a table there, but somehow something smart that allows us to read and write efficiently. Any guess? Yes? No, this is like if you do an export port, you mean like a CSV file, right? Yeah, and these CSV files are fine for an export, but when you have your real database, it's not stored in a CSV file. Maybe you have a small CSV file that you process in a Python script, but if you have a large database that is gigabytes or terabytes large, you don't have one CSV file for this. But the data structure, but you can use CSVs often as exports, for example. So the data structure that you use is some type of a B tree. So it's often some variation of a B tree, of which there are numerous. So it's a B tree. B does not stand for balanced, because balanced trees, there are lots of other ones, but a B tree is one type of a balanced search tree that allows us to store and query and manipulate data efficiently. And this is used in some variation in our internal schema in most relational databases. And then we have the database management system, which runs on top of the actual database. And its main task is to manage transactions, because we may run multiple transactions at a time. First of all, we may have not just one query, but we have a few queries combined. And we want to run this as a transaction. And a transaction means if one of these queries or one of these updates, for example, fails in between, then the whole transaction will be unrolled. So a transaction can either be fully completed or not completed at all. And the idea of transactions is that you don't want invalid databases or invalid values, because if you say you have three queries that somehow update your database in a row and they depend on each other, and you run the first one and it works, and you run the next one and it fails, and the third one is not run, but we have run the first one, maybe also just part of the second one, then we have an inconsistent state that would be very, very hard to fix. And that's why in database management systems, we have transactions, and either the whole transaction is completed, or if there's an error in between, the changes you have made will be rolled back and they will not be effective. And then it can become more complex in a transaction manager, that you have not just one transaction, but multiple transactions at a time. Maybe you have a super lengthy transaction that changes some tables, and you run other transactions in parallel that read from totally different tables. That's fine, because they work on different tables. but maybe you have other transactions, so they can be run in parallel, but maybe you have other transactions that one transaction works on a few tables and the next transaction works on some of these tables as well. So they cannot be run in parallel, but these transactions are run in a sequential way. And because you, as the programmer who uses the database management system, you don't want to deal with this, this is done by the scheduler in the database management system. And there are a few more things like the recovery manager, so you're able to undo some of the changes. But once your transaction has passed, you actually want to write it and you want to have your changes in a durable form. And there should also be some logging and some buffers to speed up, and some logs in case something goes wrong. So these are the key pieces of a database management system. And another term that is important just for the revision or just a key essence, because then we will contrast all of this to big data systems, is an index. An index in a relational database is a structure that allows us to run queries faster, because maybe we have some column and we want to make decisions based on a column value. So we want to query rows based on the value in a certain column. And if it's an integer, this is probably quite easy to find the right rows, because we could try with an index, we would be able to quickly locate the data, and we have to compute this index at the moment when we write into the database. So an index allows us to speed up queries. But the index also needs to be amended when I amend the data. So an index always leads to some extra work when I make changes to my table. But index are usually quite helpful for certain columns. If you have a key is typically immediately also an index, so we can do quicker lookups rather than doing random lookups when we don't have our indexes. So indexes, they can help us to bring some data, for example, in order or in structure, and we can query much quicker. And the next point that is important to relational databases is normalization. Who of you remembers this from your database class? Good, at least some. Imagine we have a database like this that stores skills of employees. And our employees, they have an ID. So the ID is stored in a different table. And we want to store more information in this table about the employee. For example, the address and the skills. It's not a very smart way to mix this up in a table. What can happen is maybe my employee relocates to a new location. And I have the address of the employee 519 in multiple rows. It could happen that I only amend some of these rows, but not all of them. And this would lead to inconsistency. So I would have multiple addresses of the employee at the current time, but only one of them can be right. So what would be the easiest way to fix this issue from the design phase? What should I do? How should I change this table? Yeah. Yes, we would split out the address information. So we only store the concrete address once in a new table. And wherever we need the address, we just put a foreign key from our table to that new table. So once the employee moves, we only need to change one entry. And this is normalization, and normalization allows us to reduce redundant information in tables. Normalization is crucial, and there are lots of different normalization forms of how far you can normalize. And it definitely allows us to reduce inconsistencies. This normalization also has some drawbacks, or there's some negative consequences of normalization. Yeah. So the normalization would take more space, especially if these tables are very empty. Do I understand this? Yeah, this could happen if we create a lot of extra tables and they just contain maybe one entry. Overall, it contains more space. Yes? Someone has their mic on. Do you want to talk with us?
Reads might take longer because I have to join the new table then.
Yes, that's correct. Thank you very much. Joining new tables. So doing queries can actually become slower because I have lots of extra tables suddenly and I need to include them in the joining, and this can make actually the running of queries slower. Thank you very much for the comment. Yeah, it increases the complexity. That's true. But overall normalization is helpful. The question is only of how far you should normalize, and there are all these different normalization forms. Don't always go for the ultimate extreme because probably maybe it's more normalized, but it makes your querying super slow. So depending on your exact use case, you need to find a compromise of how much normalization you do. And then when it comes to relational databases, there are some key properties that we will revise now or rediscuss for relational databases. And later, when we look at big data systems, we will see that they come with different guarantees. ACID. Who remembers this or has heard about ACID? Just a few. It should be discussed in your database course, I guess. Now, the relational databases, they come with various guarantees. For example, I mentioned the transactions before. And the A in ACID stands for atomicity. And atomicity means that a transaction is considered one single unit that is either effective or not. And if there is some error in between the transaction, what has already been done in the transaction will be rolled back. So a transaction can never run through partially. It can either totally fail and then it will be aborted, or it can totally succeed. And this is a super important property of relational database management systems. Then let's maybe continue with the D in the last letter, durability. Durability means once your transaction has been completed and it's committed, then the changes are really in the system. No matter what happens next, if there's a power failure or a new error, once the committing is done, the changes are in. So it's not just that you have made your changes to some buffer and then, I don't know, there's a power failure and your buffer is gone. Once you've completed the transaction, you committed it, it's in permanently, not just temporarily. Then the C stands for consistency. And consistency means that your transaction brings the database from one valid state to another. So this is closely related also to the atomicity, yet with a different focus, because you have your guarantees in it, or you have these invariants, for example, saying you require certain types in your columns, you have foreign keys and all of this. And when it's consistent and your transaction finishes and is committed, so there was no error in between, then you again have a consistent state. And if your queries in the transaction, for example, would hurt consistency, for example, putting impossible values in a column, then the whole thing would abort, but you would not be suddenly in an inconsistent state. And isolation refers to the parallelism. Before I talked about the transactions, and we said we can run transactions in parallel, and the isolation means that, yes, we can have parallelism of transactions, but the result will be exactly the same as if we had run these transactions sequentially. And I mentioned before, maybe I have two transactions that work on totally different tables and both need very long to run. We can run this in parallel. It's absolutely fine because these transactions address totally different tables. If they work partially on the same tables, Sometimes we can parallelize it if they work, for example, on totally different rows because the conditions are totally different. But if they would work on the same rows, then we cannot run this in parallel. So the scheduler will run the first transaction that was first submitted first, and then the second one once the first one is completed. So we would have the same result as if we first run or send to the scheduler the first transaction, wait until it's done, and then send the second transaction. So there are some things you can run in parallel, some you cannot, but the database management system takes care of this for you. It's overall something very helpful. And these ACID guarantees are one of the reasons why relational database management systems are still so popular today. So I already remember when I finished high school and started at university in 2008, there's already a lot of rumors, these big data systems, they would replace all the relational database management systems, and it would only take years to replace all relational databases. But now, 17 years later, the majority of database systems around the world are still relational because the relational ones come with these very good guarantees. And yes, for some use cases, we need different systems, and that's what we will see today and next week. But the relational database systems will probably still be there in 50 years in some variation. And they too have been improved to scale to very, very large amounts of data. Because first of all, when you have these guarantees, this could lead to a reduce in runtime. So it would take long maybe to run certain things. And it may appear that this doesn't scale to very large amounts of data. But there are obviously lots of tricks what Oracle and others have done to make these systems scale to very large amounts of data and still run very efficiently. For some problems, yet maybe other systems could be preferred. But I would say still from today, 50 years from now, relational database systems will probably still play an important role. Maybe they won't be the dominant one anymore. I don't know what's in 50 years, but I don't think they will just suddenly disappear because this is something I've seen people arguing for the last 17 years and it has not happened. But for some use cases, you may need different database systems. And that's what we will do in this chapter. And we will not just look at databases, but at distributed systems. If you want to practice your SQL skills, there's a very interesting game on the internet. It's the SQL murder mystery. So you can run this in the browser, I think. You don't need to download anything. And you work for the police, and there's a crime scene, and data and evidence from the crime scene has been collected in the database, and you need to figure out who the murderer is based from the evidence that is stored in the database. Anyone has played this game before? Okay. Okay, or a different game. There's lots of games like this. I like the murder mystery a lot. It's been very popular for many years. So if you want to practice your SQL skills, this should maybe take you, I don't know, 15 or 20 minutes if you have practice. It shouldn't take very long, but it's just an interesting application. And one student sent to the chat some other game, SQLnoir.com. So as one word, which I have not played yet, but feel free to try this. Now we're coming to distributed systems. And in reality, you will not be, it's also what we said for the motivation of this course. In reality, you will not be doing all your machine learning problems on a single computer with all the data fitting in your hard disk and your RAM, and that you could run all of this on your local machine. Because these computations may just take too long. Maybe your RAM, your disk space is too small. Well, what happens if your computer crashes? Then if you run some web service from your local computer and your computer crashes, then your service is down. And if your hard disk dies, your data is gone. So we need something different in reality. And for this, we use not just one machine, but we use a distributed system. And in a distributed system, we would have a system which has various components that are located on different networked computers. And these computers, they will communicate with each other and pass messages to each other. From a very generic perspective, this is what a distributed system could look like. We have 4 computers, and on each computer, we may have a totally different operating system. Maybe one computer is a Windows computer, the other one maybe uses Mac OS, and the other 2 use 2 Linux distributions. Yet we want to glue all of this together as one big distributed system, and we don't want our actual applications to bother about this, because our applications that we are running, it's just software that you want to build that does, for example, some machine learning task. You don't want to bother with different operating systems and how they communicate with each other. You just care about your services running. So what you need is in between a distributed system layer, which is often called a middleware layer. And this one would run on each of the computers and interconnect and sort of build an abstraction so you don't need to deal with the local operating systems or with network special issues, but rather your applications only use this distributed layer, the middleware. And then you could have one application running on one computer, maybe one application is distributed among 2 computers. On one computer, we may have multiple applications running. So this is actually our setting that we want, that we don't need to deal with the hardware and the network too much, but rather this is done for us. And this form of distributed system here is very generic. And one concrete variation of this is cloud computing. And cloud computing has become very popular in the last 10 or 15 years because it's, again, a further abstraction, because we we don't need to think just in local machines that deal with each other, but rather in the cloud, we reserve computing space on a virtual machine, and we create these virtual machines and say, I want a computer with 4 cores and 20 gigs of RAM and a hard disk and some other properties. And I don't care even about the local computer, how this is realized, but rather the cloud environment, which is something even more abstract than what we saw in the middle layer, that manages for us how this virtual machine is eventually realized. So obviously, the cloud provider needs to think in terms of local machines and say, I have 500 servers here and 500 servers there and different ones, and I interconnect them. But the cloud just provides abstraction to us because we create virtual machines. And this is super helpful because we pay for the virtual machines that we create and run. We can also flexibly maybe add more RAM, more cores, something you cannot do that easy on a local machine. Maybe you have to make some major changes to it. And you can make these changes maybe even on the fly without shutting down the virtual machines. That's something super helpful, because if you have a local machine and you want a bigger CPU, you have to shut down the computer. But the cloud or the virtual machines in the cloud, you don't need to do that. So this is overall something that has become very popular. And many of you have done your internship so far. Who of you worked a lot with cloud services during your internship and maybe built some machine learning applications in the cloud? So what did you do?
I did one on AWS.
Okay.
It was GPUs for the training.
Yeah. So you used GPUs on AWS. Anyone else worked with maybe Azure or IBM? What did you use?
And set up a chatbot there.
Okay. So I'm just repeating this for the audio. One student used Azure and set up a chatbot there. One person used Databricks. So the cloud is very helpful, but it's not a silver bullet. So I also want to warn about a couple of things when it comes to the cloud. So overall, I'm positive about the cloud because it allows us to scale, and we can fire up new worker nodes easily, and we can shut them down, and we can scale very easily. We don't need to make a lot of hardware investments upfront. However, if you run a lot of computations permanently, the cloud is maybe not necessarily the cheapest option. Maybe sometimes it's easier to put a few GPUs than in your local data center. And obviously, when you are in a cloud, this may lead to vendor lock-in. So especially if you use a lot of services that are offered, for example, by AWS or Azure, obviously you can run your virtual machine there and you can build everything from scratch with open source libraries, but these clouds also offer lots of features on their own, say lots of machine learning features. And if you use those libraries, then you're trapped to AWS or trapped to Azure. And then if they get more expensive or change their terms, you're trapped. So this is something, maybe these features are helpful because you can build something very, very quickly, but always think about the long-term consequences. And also, they can shut you down anytime. Maybe for political reasons, something that is now maybe becoming more likely, we don't know, can happen. But also if you, I don't know, use AWS and you start building some portal there that competes with Amazon in their key business, they may just shut you down. So you can use the cloud maybe for scaling, but maybe you want a different spot to run your actual key business. Maybe you want to have the core of your infrastructure in your own data center and your data, and you just use the cloud for scaling, for more worker nodes, but you maintain some independence. In terms of cybersecurity, the cloud is interesting because if you run your own data center, cybersecurity is an issue. And you need people to do this for you, and it's going to get more and more expensive. And the belief has always been, if this happens in the cloud, then you don't need to worry about it. What do you think about this? Cloud, is the cloud always better in terms of cybersecurity? Yes? Yes, they could do something wrong, but you saw also with Azure, they had by accident released some, I think, some super keys or something, that were public for a long time, and others could have used them to cause harm. And we also have a cluster risk. What if, too many essential services around the world all run on AWS, and AWS has some catastrophic loss? Then lots of other key services, maybe your health insurance, your maps, whatever, your email is all gone because AWS failed or is down for a week. So all of this creates cluster risks. And this is something that is becoming more and more problematic. And we also saw with Azure, for example, they had some cybersecurity issues and didn't fix them. It's a big problem. So I'm not against the cloud, but just pay attention to what you're doing. When I worked in industry, we also, in the company I joined, they had negotiated to use some AI services from IBM at that time. And when I joined, these negotiations were ongoing, and somehow they didn't progress very well because the company I worked at, they were concerned about what happens to all the data, the insights, if we deal with IBM. They wanted to make sure that IBM doesn't use that knowledge for competitors of us. And for this, you need an NDA, a non-disclosure agreement. But this turned out to be very difficult because we were only able to get an NDA with IBM Germany. And in Germany, again, they have lots of subsidiaries, not just one company, but lots of them. And you sign an NDA with them. And they follow the NDA, but the NDA does not apply to the whole IBM. So if they talk to their colleagues in a different subsidiary or in the US, then what those colleagues do may not be covered by the NDA. And I had a lawyer working on this contract, and they had lawyers, but somehow this just didn't progress because the terms we could never sort of converge. And at some point, we just made an order and we said we'll continue with this now, knowing there were some risks. But if you try such contracts, they are important, but don't fully trust them and always look at with whom you're signing. Are you signing with AWS Germany or the whole AWS? And you need to pay attention to this kind of stuff, especially what they do to your trade secrets, if they can use this for some of your competitors. What I saw in industry as well, one of our subsidiaries, they tried to collaborate with AWS. They wanted to use it more. And AWS seemed super friendly. They said, yes, we want your subsidiary to use AWS and build some AI use cases. And they even sent 3 data scientists for free for 1 month to the subsidiary, helping the people there to get to know how AWS works. And they built some use cases with them and some prototypes. Does that sound friendly to you, or would you be cautious? I told them not to do it. I said this would lead to lots of trouble, and it did eventually, because, well, no one is sending 3 data scientists for a month for free, just hoping they make a little bit of revenue with you on the cloud. But yeah, the AWS in that case didn't know much about these problems from mechanical engineering that the subsidiary was working on. And yeah, they wanted to see what such data sets would look like, and some domain problems we were facing in mechanical engineering. And a few months later, the prototypes they built were available as ready-to-use features in the cloud, also for our competitors. So I warned about this from the beginning, because I didn't really know what the consequence of all of this would be, but I just felt no one is going to send 3 data scientists for 4 weeks for free, just hoping they make maybe 50,000 revenue per year with the subsidiary. So probably it was not such a smart choice. And the other cloud vendors do similar stuff. So pay attention to this kind of stuff. No one is going to send 3 free people for a month. They definitely want your domain knowledge and your trade secrets. They may not steal it, or they may not copy paste the data, yet they may get inspired to what you're doing and build expertise in something they had no clue about before. So I would be very suspicious about this kind of stuff. What I want from you is you also have a homework. We have this MapReduce paper, and we will discuss it next week. Next week, we'll have the lecture as usual. And MapReduce is an approach that Google proposed some 20 years ago about how parallelism could be done more easy than building your own threads, your locks, and synchronization. And the MapReduce approach is something that's been adopted ever since and is now the foundation of a lot of different computational models. And we want to discuss the original paper. You find it in Nextcloud, and take a look at it. And we'll discuss it briefly next week and probably have a better discussion about how MapReduce works. After that, we will look at the CAP theorem. We will see some fundamental limitations that any distributed system has. And then we look at a couple of guarantees of big data systems, like we looked at ACID today, and take some time to revise ACID again for relational databases. And we'll contrast this to Bayes. And then we look at efficient training using different hardware. And we're done for today. And I look forward to seeing you next week.